Okay, so let's dive into projections, transformations, and what actually makes our graphic scenes interesting. So in principle, operating systems always have some very basic graphics capabilities. Something like set a pixel at a certain location of your screen at a certain color, or set a pixel in a certain window to a certain color. Maybe some of them also have primitives like draw a line from here and there. After all, they also need to have these kind of graphics capabilities for their UI if they have one. And so this is what you expect to find. But this is of course not practical for real applications, because you would need some way to work out how to set every single one of these pixels to represent something you expect, a 3D object, for example, like something like that teapot. So how would I actually now work out that this particular pixel on your screen is blue here, and this is white, and this is more blue. So this is really the essence of graphics, and how to get from a representation like this to a representation like this, a list of pixels that we set in certain colors. So first of all, we need some frame of reference, and usually what we do for this is to agree from the very beginning on a world coordinate system. So the world coordinate system really starts with what sort of unit do I expect. Do I measure everything in meters, in centimeters, millimeters? What does a pixel, for example, represent? How big are they? How big are what are distances? We could be light years in a universe to microns on cell level, or even atom level, even smaller. It doesn't really matter what you choose. The key thing is that you are consistent across your application with your metrics. Now, what you get from your operating system is usually something like a drawing area, right? You have probably a bigger screen, and within that screen you get a drawing area by the operating system, which, well, it depends a bit what operating system you use, but it has its own coordinates, either relative to the screen, or very often you would normalize to these drawing areas and then start your pixel coordinates at an origin like 0, 0. Now, there is maybe also something to consider which is not quite obvious. That is, how do you take care of things that are not visible? Right? I would assume, as a application developer, well, these are things the operating system should actually take care for me, right? So the areas, if I ask the operating system to draw somewhere, say -10, 10 relative to this drawing area, up to somewhere also outside of the drawing area, then the operating system should probably clip away the parts which are not visible within the window and just draw this. So the issue with this is that the operating system really doesn't know at this level what is going on and what is being rendered. So it doesn't know my scene definition, for example. If I would, if it would whatever take in front of you as an entire scene definition, then the operating system really can't know, and the only chance you would have is to throw every single primitive that makes up your scene at this pure drawing area and try to work out the operating system if it's inside or not. So there will be, I would guess, more than 90% of the coordinates in whatever room you're, for example, are not in your view, thus would not need to be rendered. So surprisingly, in graphics, this is also something we need to take care of. We need to work out what areas of my scene are within a viewing frustum, are visible, and should then be converted to pixel coordinates and to colors and so on to show an appealing scene. Now, now, what you probably want to achieve with computer graphics is to write programs that produce images that look pretty much the same independent of the device you're using. So you and your friend might have both a laptop, but the laptop might have different screens, where different screen resolutions, so different number of pixels, different color representations, or very, very different on a very bare bone hardware level. But at the end of the day, you want a teapot to look like a teapot on both screens. And if you have defined it as blue, probably you also want to have more or less the same type of blue on your screen. So a general requirement in graphics that we have something like device independent graphics commands. Things that are relatively defined, things that allow us to process graphic scenes as much as possible in an abstract level, in a device independent level, until really the device then needs to take over and convert whatever commands we have, like the draw pixel commands, into their own screen. So that also means we need to take care of actually a lot of things in graphics pipeline ourselves. So usually the very low level graphics commands and graphics environments always work somehow like this. We must ask the operating system for the pixel addresses of the corners of the area we are using. So this is the drawing area. So relative to the entire screen, we will have somewhere an area where our drawing area begins. And then we can translate our world coordinates into this drawing coordinates. Right? This is just a very primitive linear operation. It's really just taking these relative distances here from 0, 0 to wherever my window starts, and then weighing all of my screen pixels I want to draw with this, so that I can get back again coordinates that are in between 0 and 1, right? I can always scale down my coordinates to this area and never go beyond 0 and 1. Yeah, so this is how you calculate it. I mean, have a look at it. This is really straightforward. This is just linear interpolation, right? It's a linear system of equations, and all you do is really scale everything down to something like normalized device coordinates. Yeah, so this is how you set up the system of linear equations to do this. This is really just a Newton linear interpolation to put your coordinates into normalized device coordinates that run from 0 to 1 in x and y coordinates. Now, something probably more important, because, well, most of the time you won't work at the level of pixel setting and figuring out pixel coordinates. That's something that your graphics pipeline, of which you are in control, but that's something what your graphics pipeline will do for you. Interesting is probably also how data in graphics is represented. And many graphics applications use scenes that consist mainly of planar polyhedra. There are other ways to represent stuff, mathematical ways, volumetric ways, and so on. But really, if you play computer games or anything, or probably also most of the animated movies right now, they all consist at a very, very low level of planar polyhedra. So these are three-dimensional objects whose faces are planar polygons. And these polygons is probably something you are familiar with. These triangles make up pretty much everything you see in 3D scenes nowadays on a computer. Of course, the problem with that is, how do you represent curved surfaces with planar faces or facets? Well, you can't, of course. You can only approximate, which means you need to make your faces very small to produce curved surfaces that look reasonably realistic. Right? The smaller you make it, the better the approximation, the better your images will look. Now, this also means that you will have a lot of them. Right? Processing one triangle is trivial on a CPU, but processing 1 trillion triangles is not that trivial anymore, especially if you need to do it in real time, as required, for example, in a computer game, or at least reasonably fast enough to render your movie so that it's still getting in onto the big screen within a reasonable time. Okay, so how do we represent these sort of faces? And this is maybe quite interesting. Um, so we need a mixture of data. First, well, we can represent numerical data, so actual 3D coordinates of vertices. So we could do it like this. We could just say, okay, I have a Cartesian coordinate system, and each of these nodes have particular coordinates. That's how I would usually probably define a triangle in a fixed coordinate system. The other thing I need is somehow to know the topological data, and that's kind of more important than it's obvious. You need to know how things are connected. How are these nodes connected to each other? So here in this case, apparently 1 is connected to 2 and 3, and 3 is connected to 1 and 2, and 2 is connected to 3 and 1. In a triangle like this, there is only one way, but if you then build a 3D object like this polyhedron here, then I also want to know 0 here, so I also need to connect 0 to 1 and to store that 0 is connected to 2, 3, and 1, right? And 1 is connected to 0, 3, and 2. And now you can scale this up to whatever dimension you want. The more of these triangles you have, the more complex that neighborhood will become, and you need to store it somehow. So what you do at the end of the day is that you store the index with its location. So these are the coordinates of your triangle nodes here. And the important part is that you store an index with these coordinates, because you also store the connectivity data, so the phase data. So the index 0 here is connected from 0 to 1 and to 3. 1 is connected, is at location 1, 0, 0, and it's connected to 0, 2. So this makes up the vertex here. Okay? So we store always vertex data, locations, and phase data. Now here you have some freedom how you define your topology, but it will usually always boil down to what other indices your current node is connected. So again, index 0 here, for example, is vertices 0, like location 0, 0, 0, 1, 1, 0, 0, and 3, 0, 0, 1. Okay? So this is how you get back to the actual location. So what advantage does this have? Well, obviously, if you want to transform, if you want to move an object like this, you only need to actually touch these locations, right? You only need to update these locations. The topology won't change if you're only doing affine transformations. So we're talking about this in a second. But really what it means is that the object stays as it is and I move it somewhere else. So all that happened is that all of these points making up that object moved constantly relative to all of the other points, right? So the object itself didn't change, only the location of all of the points changed simultaneously. It changed just the same amount. Okay, so I only needed to touch these then, which is much more processing efficient, of course, as if I would need to recalculate all of this plus all of the connectivity information. So some of you might know then wireframe models. Old movies use them a lot. I have also a wireframe model of our teapot here. I don't know if you can really see it. And so in order to draw this, really all we need is we need to first convert the points, all of the points of these triangles in here, we need to convert them somehow to a 2D representation. I mean, some of you might already see that my camera here is doing this for me somehow. Right, so probably we should work out how our camera works here to make the whole thing happen synthetically again. So then we can use our drawing primitives, points and lines and so on to just draw them on our screen. So the conversion from 3D to 2D is called a projection. And you might be very familiar with that. This is a concept from discrete math, which you should have used quite a lot to process data in the past. So in a projection, a projector basically, or a camera here, takes a point and projects it on a 2D surface, right? So we take our teapot, and really what it does, let's see if I can make it somehow look realistic. What it does is that all of these points get projected on this single plane here. Still, our brain is able to make a 3D object out of these points. Well, there are some depth cues missing, like stereo and so on, but we still know, well, that kind of looks like a teapot. Okay, and we still can build a relationship here between this point V, which is really in a 3D scene on our, in this case, silhouette of this teapot, to a point P in 2D here. So they represent the same thing. Obviously, they have different coordinates. They have different coordinates in 3D. And also what we can observe here is that our projection surface, the area where we project our 3D points to 2D plane coordinates, is actually part of the 3D scene. You see? So there is a plane in 3D space to which we can project. And the other thing to note here is that we sometimes talk about the viewpoint. The viewpoint is just the center of view, right? The focal point, or however you want to call it. So this is the point from which I observe the scene. So from your perspective here, it's the camera. It's your eye, basically, right now. That's why we often use the eye here. Theoretically, there is no reason why you should use a plane. A plane is just one object to which you can project. You can also project on spheres, cones, and so on. Spheres are in fact also used a lot, for example, for environmental effects, or if you, I think in Google Maps, you should be familiar with spherical projections, where the Google card basically processes a spherical projection and then synthesizes these kind of street view images for you. We can use curved projectors, for example, to produce lens effects of very distortive lenses, or a mirror that's bent, right? You know, probably these kind of freak show events where you have these bent mirrors where you look then either very, very small or very tall. But in this course, really what we want to consider first is only these kind of 2D planes, not only because they are easier, but that's what you use 99% of the time as a screen. Well, now let's quickly go back to this one slide. So we said this viewpoint is your eye, right? So it's somewhere on your side in your eye, and you're looking at me. So it's at a distinct location, and what we want to do now is probably to work out how can we convert that point V to projected point P. So what would be the equation to transform these 3D coordinates to 2D coordinates? Now, let me quickly sidestep here and show you this. So what I use in these lectures are these sort of 3D coordinate systems. So these are Cartesian coordinate systems. You're very familiar with these. There's a specific color scheme on mine, which is red, green, and blue. And this has this is not by chance. It's not really a convention, but many people do it, is to say that the red is the x-axis, the green is the y-axis, and the blue is the z-axis. RGB, X, Y, Z. So that's the idea. There's one thing to consider. We will come across this from time to time. What I can do with coordinate axes, I can define them somehow arbitrarily. I can say the x-axis goes relative to these two positive axes to the left, or I can say it goes to the right. I can take it and put it on the other side, right? It's also a valid Cartesian coordinate system, but everything would work flipped in this way, in this one, if the positive axes are now going to the right here. So there are conventions in OpenGL. There is no right or wrong, really. You choose one, you only have to be consistent. So for now, let's probably choose this, but it's really just for illustrations. Now, okay, let's see what's happening here. If I put the viewpoint here on your side, right, on this side, then what we can discuss is where is this viewpoint, right? You can now take a measuring tape and measure how far your eye, your head is away from your screen, and then probably guess how far I am away from my camera. So there is apparently discrete kind of measurable value between the eye point and this projection plane. But what if we say, well, why not putting that eye point completely into infinity? Why not putting you into infinity so that all of the virtual viewing rays that go from your eye hitting the plane I'm projected on going to become parallel? So this would look like, it's a bit like this, right? So all of the viewing rays coming out of your eye, if you would imagine this like viewing rays like this, that come out of your eye, hit me somewhere here, then all of them become suddenly parallel. What this would give us is, probably we also need another assumption. We can also say, okay, our viewing plane is at Z0. So our viewing plane lives in the XY plane. Okay, so this, if you now take me as your viewing plane, what this does is that your origin is somewhere in the corner of your screen, of this small area here. The viewing direction, that blue one, looks into my scene, right? And the projection is back there. So you are in Z equals 0. Now let's assume you are infinitely far away. So all of these blue viewing rays here are now becoming parallel. Obviously they aren't, because if I move this, you see they can't be parallel. But let's just assume for the moment that they are, just for simplicity. So all these blue rays here, all of these viewing rays have the same direction, and let's say they are 0, 0, minus 1. So let's say they're all coming from the origin, and their direction is going into -1, which is my direction. This minus is a convention, but it makes things a little bit easier, because you go beyond the scene. Everything which is below in your direction is positive. Okay, now, so the only thing we need to work out now to get from V to P is an equation like this. We have a parametrized line here. We have this viewing ray, and that viewing ray somewhere meets me. A parametrized line you are well familiar with. So this is just point, so origin, or wherever we start in the scene and on your side, go in here until it hits. So it's just a point plus a scaling factor times a direction. So the direction we know, it's 0, 0, -1. The direction needs to be normalized, which it is in our case. So 0, 0, -1 is normalized. So we only need to scale it and work out the scaling factor to find the projection coordinates of, say, my nose on your screen. And really all we need to do is to subsidize in. We have d 0, 0, -1. We have coordinates x, y, and z coordinates for v. Because we x, v, y, and v, z. And we have subsidized in now for d. Our p point lives here. At this point we have 0, 0. So this is always 0. There are p and x and p, y coordinates, assuming that our viewing rays are all parallel. Px and py are simply vx and vy. Now the only thing we end up with working out is pz, which is vz minus our scaling factor. So the z component of our v point of, say, my nose. So again, this is the origin. My nose has somewhere x, y, and z coordinates. So that z coordinate we need and subtract mu. And really, if you think about it, it's actually more intuitive than I'm probably able to explain it. But all you need to do now is, since we have defined that plane here, right? This is your projection plane. That plane, remember, we defined lives at z is 0, right? Starts at the origin, is that entire plane. So now the only thing we need to do is to set p set 0, right? Because we know that all of our points on the projected plane live on that 0 plane. So we don't even need to calculate anything. Well, you can work out it here and substitute forth and back and so on. You'll realize that vz will always be 0 in that setup, assuming all viewing rays are parallel and assuming that the origin is in your plane here and that projection plane lives at 0. And this makes things very, very easy, right? I don't need to calculate anything. It's trivial to compute this. You will be very fast computing things like that. So it's very efficient as well. So let's okay. So this is orthographic projection, but really, so the projection is the projection on the screen is nothing else than the x and y coordinates of whatever object you have defined in your scene. So we simply take the 3D x and y coordinates, nothing to compute. We just take those and we know where to render. So this makes the orthographic projection quite useful and simple, but probably not nice enough for things like computer games or movies and similar. So this is how it looks like. If you look at a cube front on, then an orthographic projection would, well, produce edges that are all parallel, of course. So if you look at the real cube in the real world, you know exactly that this doesn't look exactly like this. So that projection is not, there's some depth actually missing, right? Because you have no chance to work out what the depth is from an orthographic projection with your intuition of the world. Okay, so when you can use it when most objects are at the same distance from the viewer, so it's used a lot in CAD applications, probably architecture drawings, but this here, for example, this is not an orthographic projection, right? So you can clearly see that this has no parallel lines. So this will not do for computer games or any other of these kind of more demanding work. So instead, we use something called perspective projection. And perspective projection takes the one thing into account which I mentioned at the beginning, your actual distance. So your eye point has a measurable distance from the projection plane. And if you take that into account, all sorts of interesting things happen. So let's assume your plane now lives at an actual distance from the origin. So let's just take this, move it a little bit, probably for in the front or in the back, and you're now living somewhere parallel to the XY plane, okay, parallel to it, but somewhere further away than at the origin. Also, your eye point is not infinitely far away. We say in this context that your eye point, just for simplicity, you have the viewpoint, lives now in the origin. Okay, so I move this little bit back towards your eye point, so now it's in your eye, and your projection plane is now somewhere more on this negative z axis. Okay, so what happens now is that all the view rays hitting me are starting in a real viewpoint, right? They are not parallel anymore, these view planes. And what it also becomes probably obvious is that if you have this parallel plane at a certain distance, that distance, if we call it f, has a big influence on how this projection will actually work out from 3D to 2D. So if I move this a little bit more into the back, the f gets bigger, then apparently the distance between these lines here also gets bigger, and my object projection gets bigger. If I move this, if I make this a little bit smaller, and move this more towards the origin, then the distance between the lines is smaller and my object projection will get smaller. And that F you might be also familiar with from photography. So that F has a real meaning here. And the smaller your F is, the smaller your focal distance is, the smaller your objects will be, the wider your field of view will be. All right, so this is quite interesting. I have an I can't actually read right now what's my F here right now. I think I'm now working on 2.8 millimeters. So the value on its own is meaningless, but you could work out the field of view from that information. And if I would tell you how many pixels I actually project to, then you could work out the actual distance here and how much this size, how far these points here on your plane are in my real room. But we are not here to do this. We are here to produce synthetic images. Now, how do we work out 3D to 2D projection in this context? Again, we have some sort of parameterized line direction. And this time the projection equation is really just a scaling of our 3D coordinates, because all projectors go through the origin. At the projected point, we know one thing again. So previously in orthographic projection, we knew that all our projected points live in the xy plane, so it's 0. Now we know they all p sets must be the same. All p sets are at that f, right, at that f distance. So they all become f. So we know this already, and now let the value of mu at this point, at that point where the projection happens, be something like mu projection, mu p. Then we can simply work out the mu p, what it should be. So it's the fraction between p set and my viewpoint set. Right? So p set is the same as f, so it's f over v set. So it's a one-to-one, it's a scaling factor. But that scaling factor now not only affects set here, it also affects our x and y coordinates. And well, we simply scale with the same mu here, v, x, and y, and can work out that my new projected px should actually be, if I plug these things in, f vx over vz, right, depending on how far I'm away from that plane. This will have an influence, and the distance from the projection plane to the origin. And py the same here, f times vy over vz. Right? So this is perspective projection, not that hard. You just have to consider 2 more scaling factors. And suddenly things look more realistic. See, everything that kind of parallel with our viewing direction becomes now directed towards our view plane. Also this is an interesting effect here, right? If you look at the blue axis, and if I move that, it's by no way parallel. It actually looks like tilted always towards me here, which is our viewing frustum box, right? So it's exactly the same as the edges here. So these edges here seem to be pointed inwards. The same I can see here. All the corners here are pointing inwards. So let me adjust my very primitive color chroma. The problem here is that sun is rising. So I need to adjust this, and sun is coming out behind the clouds. So I look a little bit more strange now. Okay. So let's keep this for a while, and then we'll readjust. Okay, so now our boxes look more realistic, and I can do something reasonable with this technique. So if you like, you can try to work that out, pause the video, and have a go on this. It's pretty straightforward. All right, so you only need to really plug these in again. The V's, X, Y, Z goes in. Our view plane is at Z5, so our F is 5. So it's 5, 10 over 10 is 5. Py is again 5 times 1 is 5. Orthographic is is 10 and 10 because we just leave out the set component and just take it as it is. Okay, so thing is, if you start to design scenes, then they are defined in a certain coordinate system. So, shut out the sun. Let's continue. So in graphic scenes, when we define them, we probably want to define them in a certain coordinate system. So we want to have that teapot probably only drawn once. Maybe it lives in a coordinate system like this in its own world, right? And we only want to draw this once. Now we have just defined that if we look down always a specific axis, right? If we look at down this axis and then look at our teapot and project it somewhere to a plane that's parallel to the 0xy plane, that this makes things pretty easy, right, with the projection. Now the thing is, now if I define my teapot in this very static coordinate system, I can only look down this particular axis. I would need to redraw and redraw my object here to get new views, new angles. Well, of course, I don't want to redraw this. What I want to do is to transform that viewing coordinate system to be able to look at this object or at my world from arbitrary angles, but mathematically always the same way as we just discussed. Always look down that particular one axis at that zero projection screen. So we need to be able to transform the coordinates of a graphic scene. So first we had this scene what I just tried to show you. We are looking down the z-axis at this object, and what we probably want is to look now from a different direction here. The viewpoint, we want to move that viewpoint here, but our viewpoint generally lives in the origin. So we need to move the origin and all of the rest of the coordinate system to be so to have the z-axis, the axis we look down, parallel to our new desired viewing direction, and the viewing coordinate system, the origin, at that viewpoint. So we want to work out this transformation from this coordinate axis to here. So we also need transformations for other purposes. We want to animate objects. We want maybe multiple instances of that teapot, but at different locations. We need that for reflections, other special effects. Transformations are really the key concept in computer graphics. So we will need that a lot. So how do you transform a single point? We will use matrices for that. And most of you probably are familiar with matrix algebra, and many of you might have already worked out what these kind of transformations are good for. They are also called affine and so on transformations in linear algebra, but often mathematicians forget to tell you the intuition behind these things. So if you work slowly through that, really what a matrix vector multiplication like here does is to apply a transformation on this point. So if you plug in the matrix vector multiplication equation, so row times column, and then go through the multiplication and summation. If you plug it in, then what you can work out here is that this does nothing else than having a transformation here, like scaling this x by 2 and scaling this by 2 and scaling this by 2. So each of these components is just multiplied directly here, but plug it into the matrix matrix vector multiplication matrix. So 2 times x plus 0 times y plus 0 times z, and then 0 times x plus 2 times y, and so on. You see what I mean. So this transforms this point to this new point. Okay, this is always how we work with transformations. And apparently this point is now, if this is at, I don't know, if this is at 1, 1, somewhere 1, 1, 1 here, and I apply this transformation, it's now at 2, 2, 2, right? So it's moved in all directions equidistantly far away from the origin. Now, a lot of transformations will require something called translation. So we move something linearly, but really the issue now is if I say I want to just move something from say 0, 0, 0 to 1, 0, 0, right, just over here. If I want to move it here, then all I do here is to have a new position x here, which is x plus something, x plus 2, for example, y and z stay the same. But how can I do this with a matrix? So I just showed you the 3 by 3 matrix times 3 by 1 vector. How can I do this? If you try to work this out, you will have a hard time to really find a matrix that fits that. Except you use a trick, and the trick, many of you will know already, is adding a dimension. And we just go to 4-dimensional space and do this operation, because all of our 3-dimensional parts here are just a slice of 4-dimensional spaces. So we add a fourth ordinate to allow to use the columns for translation. So what I get now is a 4 by 4 matrix times a 4 by 1 vector. And now I get suddenly another axis here, which allows me to plug in my translation. Because if you put that again in the matrix vector multiplication equation, then what you can work out is that this is nothing else than x stays here, x in the diagonal, plus 0 plus 0 plus 2, right? So this moves now by 2, and then here I have plus 0 plus 0 plus 0. So these are all 0, and then that last one does basically nothing, right? We have 1 here. Really what it is a scaling factor, so I can scale things here again, forth and back, but most of the time this will be actually 1. And really the way I go from 3 by 3 matrices or 3 by 1 vectors to homogeneous coordinates is I add a 1, or in the matrix case, a row that looks like this, 0, 0, 0, 1. The vectors have a 1 here. There are more caveats to it, but for now, let's leave it with this. That we can do homogeneous point coordinates always like this. And going forth and back is trivial. Really, you only add a scaling factor, in this case 1 in our case. And if you want to go back to Cartesians, you have to take this scaling factor and divide every other, all the other components of that vector by that scaling factor, and you're back at the Cartesian coordinates. Okay, so what we can model with a matrix like this are affine transformations. So affine transformations are those that preserve parallel lines. So as I said earlier, all of the points in my object here, all of the connections will be preserved. They will, if they were parallel before, they will be parallel after the transformation. And most transformations we require are actually affine. So the most well-known and obvious ones are, I want to make an object bigger or smaller, scaling. I want to take the object and rotate it. So this is an affine transformation, or parallel lines preserved. I want to translate it around, right? There are more other complex transformations I can't show on a physical object. I can share them and tilt things, but really rotation and translation and scaling is are probably the most important things you'll need in this context. An example for non-affine transformations is what we just discussed before, a perspective projection. Parallel lines are not preserved if you apply this as a matrix, but you can formulate it as a matrix, right? So but it's just not affine. So yeah, this is what I said. If I look at a affine transformation matrix, so you can split that up into regions of certain semantic meaning. So that region here in our affine transformation matrix, that column, this is only responsible for translation. Again, if you plug it into the matrix vector multiplication equation, what you end up with is always this point x, y, z plus the value whatever is there. Right? So you can also use the scaling factor. If you put in 2 here, it will become interesting. You have everything scaled by 2 at the same time, which is only valid for this translation. Very strange. I wouldn't do it. Leave it with 1, because scaling you can also do by just setting all the diagonal elements here to a value larger than 1 or smaller. Then you scale. So these matrices are all invertible, so they all have an inverse. Really intuitive if you think about translation, what I just showed. I translate by 2 in x. Well, how do I invert that transformation? I invert back the same amount, right? I invert back by 2. So I have the inverse of this matrix. So I can also always work out these inverse operations, and they always have inverse matrices. So if I have a translation matrix like this, the inverse will always be this minus the same factor. Well, you can sit down now and build the product of these two matrices, and then what you will figure out is that you end up with the identity matrix. Of course, just plug it in, tx minus tx plus tx, and then you get 0. So trivial. Okay, scaling is what I already mentioned. Scaling is better than here, because this scales regarding to the origin of where you started. So this is something you really need to be careful. All of these operations are, of course, with respect to the origin here. So if you scale now, and I would need a balloon now, but if you scale now, you would scale with respect to the origin. So you would scale basically in this direction up and then make it bigger. It's not like intuitive scaling, like from the center point of the object. That is something you would need to do yourself, produce yourself. We'll talk about that in a sec. But anyways, scaling is diagonal elements all the same. So this is, for example, 2, 2, 2. Then I scale by a factor 2. And what this does is it multiplies all of my coordinates by 2. So moves it away from the origin. The inversion is just 1 over the scale factor, of course. If you multiply with that, then you can undo this multiplication with the division here. So suppose we want to make an object centered at the origin twice as big, and then move it so that the center is at 5, 5, 20. Now this is something you will always need in that context, because as I just said earlier, probably you don't want the effect like scaling be related to your origin. You want it probably related to your object. And what you then often do is to move the object first to the origin, perform your transformation, and then move it back to where it was. So now in this example, it's combining two matrices to do a certain operation, like move it, scale it first relative to the origin, and then move it to a certain location. And you can always concatenate and these matrices and multiply them together to make one single transformation matrix. This is again for efficiency reasons. You probably only want to multiply one single matrix with all of your millions of points in your scene, instead of multiplying 30, 40 matrices with all of your points individually. So the way you can do it is you scale first. We always go right to left. So we always go right to left. We have the point here. We scale, we multiply with the scaling matrix, and then we multiply with the translation matrix, which means we have the point scaled, then translated. And this is pretty important, because all of these matrix multiplications are, of course, not commutative. So they don't commute, so you can't just swap them around and expect the same result. We'll talk about that also in a couple of slides. So if we multiply matrices together, we get a single matrix and have something we can efficiently apply to the expected million points in our scene. Again, that is very, very important. Transformation matrices are not commutative. T times S is not the same as S times T. Just think about that in a concrete example. So if I have an object sitting at my origin here, okay, and I move it by 1 and then scale it by 2, or make it bigger, I can't make this one bigger, is something different than if I would scale it first and move it then. It's probably easier to show on this box here. So the box moved first and then scaled relative to the origin, so I end up with something ending up here at 4, while if I scale first, I only scale to this point here, and then I end up, if I move by 1, at a different location. So these results are vastly different. This is probably the key error source when doing graphics programming. Not being aware of your transformation matrices, not having worked out the correct order of transformations done. It's really hard to debug as well. Okay, rotations. Rotations are relatively straightforward. All I need to do is to work out the individual rotation components, clockwise or anti-clockwise, around the individual axis of your coordinate system. So I can build up a rotation matrix of 3 individual rotation matrices, each rotating around one of the individual axes. So I have one rotating about the x-axis, one rotating about the y-axis, and one rotating about the z-axis. And this is how they look like. They look scary, I know, but they are just worked out from polar coordinates relative to polar operations in a plane. So you don't really need to memorize things like that. Usually you would either look them up if you really need them by hand, or use functions to convert from either Euclidean representations of these transformations to matrix form and forth and back, or work it out in a different way. You can work it out manually. So if I want to rotate by this phi around a certain angle here, so about each of the axes, then I would just need to plug them into the equations here. And how do you work it out? Well, it's really just the representation in polar coordinates. So x and y I can represent as radius times phi here. So the radius times phi is that angle here, and then I can work out how far I need to go from what I have already in radiant representations to what I want to have. So I add this representation here and end up with a matrix like this. So just for x and y, and this component is x and y if I want to rotate around z. So what this does here is building me the rotation matrix R z. So this is z. So I want to rotate around here, and then I end up with something that rotates, gives me a rotation matrix relative for x and y. Of course, because I stay within that plane, z does not change. I only transform every value that lives in that plane around a certain area here. Okay, so most of the time we'll stick to left-hand coordinate system. Rotation we do anti-clockwise when looking along the axis of rotation. So if we look along this rotation, then we rotate that way. Rotation is clockwise when looking back towards the origin from the positive side of the axis. So if I look down now, then for me it's becoming clockwise, right? We're going like this. And if you look down here, then you're going like this. So depends on how we look from the origin along this axis. So you see, this is probably not quite trivial if you do that manually. So most of that will be done through scene transformations that you can solve according to parameterized equations, linear system of equations, where these matrices, these transformations fall out more or less automatically. You would very rarely sit down and really work out the rotation of an object around a certain angle, or these kind of transformation matrices, because most of it will either be mathematically well defined or interactive. And interactive, you don't need to be super accurate to the millimeter. Of course, you need to be accurate, but you don't need to. You will never ask the user to plug in numerically your transformation matrices. That's what I want to say. Okay. So inversion of rotation matrices is the same as the translations. You just rotate back by the same angle, and you can use these relationships to find the inverse of the rotation, and really all of these matrices also have the have an inverse. So the rotation matrix in one direction would look like this: cosine phi minus sinus phi, sinus phi, cosine phi, and here you would flip the sign then, and then you get the inverse these two flip the sign, then you get the inverse. Again, you don't need to memorize these things. You need to know that probably the one thing you should remember is the nature of your transformation matrix here. So these parameters here, these values, define how you rotate your object around your world coordinate system. Okay, around the world coordinate system. Again, I said around the world coordinate system. Intuitive would be around the object coordinate system, but in these transformations, you always rotate, transform whatever you do around the world coordinate system. Okay, so that's it about transformations. I also have a look at probably the other lectures. The other lectures in are from 2019, so I tried to make it more suitable for a lecture hall back then. Now we are of course not in a lecture hall, so let me know what you think, how this works, and maybe I work out the chroma key here at some point.